In this paper, we present a transformer-based framework for ghost-free high dynamic range imaging. Multi-frame high dynamic range imaging aims to generate an HDR image by merging several LDR images with varying exposures. The LDR images can be well fused to an HDR image if they are aligned perfectly. In practice, however, this ideal situation is often undermined by camera motions and foreground dynamic objects, yielding unfavorable ghosting artifacts in the reconstructed HDR results. Existing CNN-based HDR deghosting methods can be mainly classified into two categories. In the first category, LDR images are pre-aligned using homography or optical flow and then fused by a CNN. However, homography cannot align dynamic objects in the foreground, and optical flow is unreliable in the presence of occlusions and saturations. The second category proposes end-to-end networks with implicit alignment modules or novel learning strategies to handle ghosting artifacts, achieving state-of-the-art performance. Nonetheless, ghosting artifacts still exist when confronted with long-range object movements and heavy intensity variations. We conclude the reason to the intrinsic locality restriction of convolution. CNN needs to stack deep layers to obtain a large receptive field and is thus ineffective to model long-range dependency. Moreover, convolutions are content-independent as the same kernels are shared within the whole image, ignoring the long-range intensity variations of different image regions. Vision Transformer has recently received increasing research interest due to its superior long-range modeling capability. However, there are two major issues that hinder its applications on HDR deghosting. Firstly, transformers lack the inductive biases inherent to CNN, and therefore do not generalize well when trained on limited data. Secondly, the neighbor pixel relationships of both intraframe and interframe are critical for recovering local details across multiple frames, while the vanilla transformer is ineffective for extracting such local context. To this end, we propose a novel context-aware vision transformer, which is formulated to concurrently capture both global and local dependencies with a dual-branch architecture. The global branch employs a transformer encoder to capture long-range contexts. For the local branch, we design a local context extractor, which extracts the local feature maps through a convolutional block and selects the most useful features across multiple frames by channel attention mechanism. The proposed CA-ViT makes local and global contexts work in a complementary manner. We illustrate the key insight of our HDR deghosting approach with CA-ViT. To remove the residual ghosting artifacts caused by large motions of the hand, long-range contexts, which are required to hallucinate reasonable content in the ghosting area, are modeled by the self-attention in the global branch. Meanwhile, the well-exposed non-occluded local regions can be effectively extracted with convolutional layers and fused by the channel attention in the local branch. We further build the HDR-Transformer, a hierarchical network to reconstruct high-quality ghost-free HDR images. The feature extraction network first extracts the coarse features through a spatial attention module. The extracted features are then fed into the HDR reconstruction network to recover the HDR results. The HDR reconstruction network consists of several context-aware transformer blocks, which take the proposed CA-ViT as basic components. The quantitative results on Palantir's dataset show that our method outperforms all the previous methods in terms of PSNR, SSIM and HDR-VDP2. In particular, we achieved PSNR-MIA of 44.32 and PSNR-L of 42.18, respectively. For qualitative comparison, here shows a challenge case that contains severe saturations and large motion. Both the compared methods fail to hallucinate the details and result in ghosting artifacts in the reconstructed HDR image, while the proposed HDR transformer reconstructs ghost-free results with more visually pleasing details. To analyze the effectiveness of each component, we also conduct comprehensive ablation studies on Palantir's dataset. To summarize, we propose a new variant of vision transformer, which can fully exploit both global and local image context dependencies. We propose a novel HDR transformer that is capable of removing ghosting artifacts and reconstructing high-quality HDR images with lower computational costs. To our best knowledge, this is the first transformer-based framework for HDR deghosting. We conduct extensive experiments to demonstrate that the proposed HDR transformer outperforms existing methods.